presentation, and this will be available on Zoom meeting in my Moodle web page. So chapter 5 is on chemical reactions. You will be introduced to chemical reactions, about reactants, products, and description of chemical equations, and how to balance chemical equations, and types of reactions commonly found in chemistry, oxidation, reduction reactions. And we also going to look into how we use moles and Avogadro number to do calculation using chemical equations, to conversion between mass to mole using molar mass taken in grams. You can use mass to mole conversion to do stoichiometry. Mole calculation in chemical equations, how to get the moles from the grams. Mass calculation, then once you get the moles, you can convert it back to grams of product or moles of product. Also, we give efficiency of a chemical reaction in terms of percent yield, actual yield divided by theoretical yield divided by actual yield multiplied by 100. There are limiting reagents or reactants in chemical equations. When you're doing stoichiometry, how to find the chemical limiting reactant, we will be going over that. You should be able to write balanced chemical equation, classify reactions according to combination, decomposition, single replacement or double replacement, define oxidation and reduction and recognize the components of a redox reaction, reducing agent, oxidizing agent, etc. Define a mole and use Avogadro number in calculation, calculate formula weight and formula mass to get the moles of material from grams of material. Relate the mass of a substance to its number of moles. That's the mass conversion to moles. Then do the stoichiometry. Carry out mole and mass calculation in chemical equation. Calculate a percent yield of a reaction and determine the limiting reactant in a reaction. Okay, physical change is different from chemical change. In a chemical change, there's a change in substance to another. In a physical change, the substance is only changing its phase or the physical form, physical state. Breaking bonds are involved in the reacting material, and making new bonds in the products happen in a chemical reaction, as given in reaction between oxygen and methane to produce carbon dioxide and water. Chemical equation is a description of what takes place in a precise form. Products are written, reactants are written on the left side with the physical state. Reactant A in the amount of stoichiometric coefficient A, that's the number of moles. B, reactant B in the amount of moles B goes to product B in the amount in the moles of C, and D in the moles of D. A and B are called reactants, C and D are called products. There's a mistake there, products. On the top of the arrow, sometimes we normally use delta sign to indicate heating. Physical states are indicated by parentheses, solid, that's solid. in parentheses liquid, in parentheses liquid, gas in parentheses gas. AQ means aqueous solution in water solutions of reactants and products sometimes. For the reaction methane and oxygen going to carbon dioxide and water, that's the molecular view or atomic view of the reaction. We have chemical equation, symbolized chemical equation of all these changes in the top equation. So balancing equation means number of atoms of each type of element on the product side, reactant side should be equal to product side. So this reaction C4H10 and oxygen going to carbon dioxide and water is not balanced. If you look at the carbon, there are 4 carbons on the reactant side and only 1 carbon on the product side. Therefore, we have to change the numbers in front of chemicals called stoichiometric coefficients until we get the balance of atoms in either side. So to balance, we put 4 in front of carbon dioxide. So then to balance hydrogen, we put 10 in front of 5 in front of water. 4 and 5. Now there's a problem. When you do that 4 and 5, there's a 5 oxygens on the water, 8 oxygen on carbon dioxide. It adds up to 13. So 13 is not a half number. Therefore, 13 cannot be divided by 2. So we have to multiply whole equation by 2. So then that 13 divided by 2 goes away. So we get 2 C4H10 and 13 oxygen and 8 carbon dioxide plus 10 water molecules. So now the atomic balance is there. This is kind of an unusual equation that when hydrogen number is even, you have to multiply by twice the equation and do the balancing. How to balance the chemical equation? Balance the equation with coefficient 1 element at a time. I did that for carbon and hydrogen. Check to make sure that the smaller set of whole numbers is used. So whole numbers, because of that, whole numbers 13 over 2, we had to multiply whole equation by 2. Write the equation with correct formulas. The subscript in the formula can never be changed in the balance equation because changing a subscript change the identity of the compound. So once we know how to balance the equation, like water, balancing equation is hydrogen and oxygen going to water. You put 2 in front of hydrogen and 2 in front of water, then the equation is balanced. Once you have the balance equation, we can do chemical calculations. The balance equation are represented by moles of material, not by grams of material. A mole is used to convert grams to moles. Grams of material is converted to moles using Avogadro number or mole of items 6.02 10 to 23 particles or atoms, molecules are in 1 mole. 1 mole of carbon atoms is 6.02 10 to the 23 carbon atoms. 1 mole of carbon dioxide molecules contains same number of 1 mole of carbon dioxide molecules. 1 mole of water also contains same number of, right? The number 6.02 10 to the 23 is called the Avogadro number. Now the question is, how do you get 1 mole of material, carbon? 1 mole of material is 6.02 10 to the 23. How do you get 1 mole of certain element or compound? You have to go to molar mass in the periodic table. For example, 1 mole of carbon is obtained by going to the periodic table and atomic mass. Atomic mass is 12.01. Atomic weight is 12.01. So that taken in grams gives a 1 mole of carbon atom. So there's a simple conversion between formula mass and what you call molar mass and the 1 mole. The value of molar mass of compound in grams equal the value of its formula weight in AMU. We don't hardly use AMU, it's called grams per mole. Atomic masses reported in the periodic tables are grams per mole. Now this molar ratio is in the balance equation and also in the formula. Molar ratio in atom is in a molecule formed between A and B is A subscript X, B subscript Y. Molar ratio is the ratio of X and Y. Molar ratio between molecules in a chemical equation are represented by balance equation, stoichiometric coefficients in the balance equation A, B, C, D. When you do a chemical calculation, which is called stoichiometry, you measure certain mass of reactant A and divided by molar mass of A divided by molar mass, you get moles of A. Moles of B, same way. Moles of C also, if you knew mass of C. Mass of D also obtain. Sometimes we start with A and B only, then don't know what C and D are. So then what you do is use the molar ratio between A and B to calculate B and C or C and D, or we can do conversion between anything, any chemical in the balanced chemical equation to convert them using the mole ratio in the chemical equation. So to summarize that, grams of a material divided by molar mass get the moles of A. Formula of a balanced chemical equation gives the ratio to convert moles B to moles A to B. Moles B converted to grams of B at the end. So normally we start with grams of reactants and end up with grams of product. But intermediary, we have to go through moles. That's how we do stoichiometry. In a chemical reaction, there's limiting reactants. Limiting reactant is just like in a recipe. For example, if you're making hamburgers, you have 10 hamburger buns, double buns, 10, 3 hamburger patties. You are limited by hamburger patties. So only you can make 3. Limiting ingredient in case is hamburger patties. Just like that, A and B require certain ratio, but if you have less, one of them is less than the ratio, that is limiting. Limiting reaction, compare A and B moles after applying mole ratio. A and B, A requires, for example, A is 1 and 2 is 2. If you have 0.5 of A, 2 of B, then limiting is A because it doesn't have all complete the reaction with B. B will remain behind unreacted. A will be used up. The reactant with the least number of moles after mole ratio considered is the limiting reactant. You can use stoichiometric coefficient, convert the moles to moles of A and moles of B, grams to moles, then compare the A and B and find out whether something is in limited quantities, and that is the limiting reactant. Normally we use limiting reactant to convert moles of the product. So it's very important when in stoichiometry to do the calculation using only the limiting reactant. Now, after we do a reaction, we have a yield of product. Actual yield is what we obtain from doing real experiment and in real time what the amount of product is. Theoretical is using limiting reactant, calculation done by stoichiometry. That's theoretical yield. So normally theoretical yield is the maximum yield that can be obtained from a reaction. Actual yield could be little less or more or less than theoretical yield. Therefore, reaction cannot have more than 100% yield, or something is happening wrong in the reaction. Actually, it's determined experimentally. It is the mass of the product that is measured. Theoretically, is the calculated mass of products based on the initial mass of number of moles of the reactants. Now, when you do concentration in solution stoichiometry, that means using a solution which has water as component in aqueous solution. You need to convert the solution concentration to moles of reactants. Use the percent concentration to obtain mass of each substance. That percent composition is sometimes used. Sometimes we use molarity. Molarity is the moles per liter. If you know the liters of solution, you can calculate the moles of material, converting molarity to moles. Then use that moles in the stoichiometric calculation. Now we're going to talk about a little bit about type of reactions called oxidation reduction reaction. Oxidation is a loss of electron from an atom, reducing gain of electrons are called reduction. Reducing agents are the one that do reduction on another compound and they themselves become oxidized. Reduction is a gain of electron by atom. Oxidizing agents are reduced. Both processes occur in a single reaction and called oxidation, reduction, redox reaction. So reduction always accompanies by oxidation. Therefore, electron transfer takes place from one compound to the other. Redox reaction involves transfer of electrons from one element to another. For example, zinc and copper. Zinc is metallic, copper is ionic ions. Now, after the reaction, electrons are transferred from zinc, 2 electrons given to copper. Copper become reduced, zinc become oxidized. So in this case, zinc get oxidized, copper gets reduced. Copper is the oxidizing agent for zinc. Zinc is the reducing agent for copper 2+. Zinc loses 2 electrons. Zinc is oxidized, loss of electron. Copper gain 2 electrons. Copper is reduced. Now in this reaction, you should be able to tell loss of electrons, and number of electrons is equal to number of individual electrons gain, loss should be equal. It's called a half reaction. Half reaction is zinc going to zinc 2+ plus 2 electrons. Half reaction for copper is copper plus 2 electrons going to copper. Now we done with chapter 5. It's kind of brief overview of chapter 5. I hope you can go through the slides and work it out, okay? And problems in the chapter 5 and will make you ready for test 2. I'm going to stop the Zoom meeting, and if you have any questions, please let me know.